Tell me when we're live.
We're live.
Okay, hello everyone. So the next speaker is Robert Rand from the University of Maryland, and he's going to tell us about Gottesman types for quantum programs. Okay, let's go.
Hey, thanks, Vladimir. So yeah, I'll be talking about this type system for quantum programs that we're calling Gottesman types for reasons that will become obvious. And this is joint work with Arthi Sundaram, Karthik Singhal, and Brad Lackey. First, let me briefly take an overview of types in general for quantum programs. So one common approach, very popular approach to types for quantum programs is linear types. Linear types have a very specific focus. They prevent cloning of qubits, and they exist in languages like the quantum lambda calculus, various versions of proto-Quipper, and Quire. Sometimes these are also affine types, which are like linear types, but allow you to discard elements. Another common type for quantum programs is what I'm calling quantum data structures. So basically, there are a bunch of languages, in particular the quantum I/O monad and Quipper, which allow you to create data types like trees or lists or pairs that are full of quantum data. And a third type, which is system, which is kind of builds on the quantum data structures, are dependent types, which allow for very precise descriptions of circuit data types because you can specify, for instance, the length of the list of qubits that you have or the depth of the tree that you're providing. The thing about these types is that these are kind of high-level structural types. So that's less what I'm interested in today. I'm interested in what you would call quantum base types. So, and there's not a very big list here. So there's qubit, and qubit's pretty boring to us because we've probably seen it a lot of times. There's unit, which is the most boring type you can imagine. It has a single element called unit. And then there's bit. I'm going to say that bit isn't that uninteresting. So what is a bit when you think about it from a types theory perspective? So what a bit is our Newtonian bit that is expected to be 0, 1. So bit can be treated as a subtype of qubit. So on our quantum computers, bits would be implemented by qubits typically. And it's just limited in that bit only contains the 0 qubit and the 1 qubit. That sounds pretty boring, but I actually find these super useful. So bits make convenient and silly. I know that they're in either the 0 or 1 state, so I can use them as such. They're invariant under measurement, which is a nice property to have if you're thinking about your program. They can be converted to Boolean values, which is really important for a program that exchanges quantum and classical control. And they can be duplicated. And while duplicability, while not present into a lot of quantum computing, is actually something that's really useful. So we have these qubits, we have bits, but there's another thing that I would like to have, and they're called, I'm calling these X. So what is an X bit? And the reason I'm calling them X might become obvious or be obvious already. So an X would be another subtype of qubit, and the minus states. And these, of course, are also very frequently used, and they're also duplicable, and they're useful, right? We use them in creating entangled pairs. And while at once I'm speaking of entangled pairs, well, there are these things called Ebits that you'll see in the literature about quantum resources and entanglement. And Ebits are defined as units of quantum entanglement, but for my purposes, they're just members of bell pairs. And they're really valuable. They're valuable for quantum communication, for teleportation requires Ebits to get a qubit over a channel. So that's another sort of base type that I would like to have in a quantum type system. So given that this is what I want, how do I propose, how would we get to having a system that has rich classifications of the different types of qubits that exist? So we could just try tracking these bits, X bits, and bell pairs, but we'd run into a problem in that we'd very quickly leave the domain that we're talking about, and basically nothing would get typed at bit, X bit, or bell pair as soon as you performed an operation on them. here's a sort of silly idea, which is let's just do the computation. Well, that's both sort of contravenes the purpose of types, which should be a lot easier to infer than what the program itself does. And of course, given that we're going to want to statically check these types on a classical computer, it's impossible to begin with. So my third thought was, okay, what if we start from Clifford circuits, which we understand pretty well, and work from there? So in order to give some background to the approach that we're taking, which is based on the famous Gottesman-Neal theorem, we have to talk about the Heisenberg interpretation of quantum mechanics, which I'm summarizing as don't think of operators as functions on qubits, think of them as operators on other operators. So for instance, we know that hx is equal to zh, and that hz is equal to xh. Well, that means that we can think of h as a function that takes an x to a z and back. And this forms the basis for the famous paper by Daniel Gottesman, in which he refers to a Neal's theorem, which we refer to as Gottesman-Neal theorem because he wrote the paper. And what fascinates me about this, more than the wonderful result that said that we can efficiently simulate Clifford circuits, is that Gottesman seems to have written out a type system. This is almost verbatim from his paper, except that I've added colons to make it clear that these are types. So these are your types for H and S and C naught on X's, padded by Y's by identities when necessary. That, it turns out, is enough for characterizing these circuits. And the only modification I would make is I would introduce, instead of saying that X has type X to Z and also has type Z to X, I'd rather have what's called an intersection type that combines those two pieces of information. So X has both types, X to Z and Z to X. So how do we get from the Gottesman sort of semantics for programs to these actually being types? So what Gottesman is saying is that an H turns an X into a Z. We also know that an X turns a Z into an X. We also know that an H turns a 0 or 1 into a plus or minus. Well then, when I say that H has type Z to X, what I'm actually saying is that it has type 0 to 1 or 1 to plus or minus. And note that these are the eigenvectors of Z and X respectively. So H takes an eigenvector of Z to an eigenvector of X. And likewise, if we look at S has type Z to Z, takes in a 0, 1, outputs a 0 for 0 and I 1 for 1. And so now I have to note that there are I's there, and this is sort of important. I can also point out that Z is, even though S has type Z to Z, that doesn't make it an identity function. It just means that it has the same domain and codomain and range maybe effectively. So I'll modify my statement a little bit. Z actually refers to all qubits that are some phase times the 0 or the 1 vector. So this is a nice characterization of the S type, of the type of S. What about these multiple qubit gates, like the control NOT? So control NOT has type IX to IX, for instance. Well, the eigenvectors of IX are really any qubit tensored with either the plus or minus qubit. And of course, that means that the output here is also going to be any qubit, or on the first wire, and the plus or minus on the second. So gives us a nice type for C naught, some Q and a plus or minus, and another Q and a plus or minus. What if we flip those? Well, this is one of the cases where the X actually propagates. So we have Xi as the input, similar to before, and note that this is something that will always be separable. And well, something on the output. So let's try to give a type to C naught. So C naught has a plus or minus in this first position and a Q in the second. And for the output, all I can really say is that it produces an eigenvector of X tensor X. And unfortunately, that's not sort of a useful conceptual category that I use for myself. But not everything will be. And we can typically get from these not useful categories to useful categories, assuming that our program produces something that we kind of would recognize. So let me give you some examples of that. So firstly, an important lemma says that for any Pauli matrix, that Pauli matrix times any number of tensored with any number of identities, the first part, the eigenvector really of the first part is separable from the rest of the state. So if it has that type, it's separable. So we can do this derivation. We know C naught has these types. So I'm now introducing an X, which says it's not the tensor. It's more of a classical pair. So we have a Z on the left and an I on the right, and these are separable, right? And the one case where I haven't done that is Z tensor Z, because that is not a separable type. So okay, I'll use the standard intersection rule to say C naught has both of these types. Now I'll use actually a derived rule to show, which allows us to distribute intersection over arrows. So, and then I'm going to simplify things. So on the left, I was saying that, if you have an input which is in both Z, the first qubit being in Z and the second qubit being in I, and the first qubit being in I and the second qubit being in Z, well, then obviously both of the qubits are in Z. And on the right-hand side, I actually had to do something a little bit more tricky, which is to say, oh, since the first qubit is separable on the left-hand side, obviously the right-hand side also consists of separable qubits. And the second qubit is, based on that tensor, a Z qubit. So ultimately, we derive that C naught has type C to Z, and that's exactly what we would want, because C naught on classical states must be classical. So this is kind of proving a basic property of C naughts, which is kind of nice. And this is actually going to be true for, if we even have a Z on the first wire, we're going to get something classical. So let's look at the one of the four cases where we don't get something classical. If we have an separable. If we have an X on the first wire and a Z on the second wire. So in that case, well, we can simplify the left-hand sides because they're separable. Nothing we can do with the right-hand sides. We'll take the intersection. We'll do distributivity. And we'll simplify the left-hand side. So what does this tell us? If we put in a plus-minus qubit on the first wire and a 0 or 1 on the second qubit, on the second wire, we're going to get out an eigenvector of this thing. In other words, an eigenvector of both X tensor X and Z tensor Z. And that actually describes something that is very common and very useful, and that's our bell pair. So that's actually quite nice. That's exactly what we wanted. Okay, now that we have that, I can start looking at some slightly more complex examples. And I'll start with the GHC, a program for creating a GHC state. So a NIT is a no-op. I'm just showing you what the initial type here is. So let's look at the case where the first qubit is in the Z basis and separable from the other qubits. Well, applying H to the first qubit will convert it into an X. Applying a C naught propagates the X, and applying another C naught propagates the X again. So we get out of that X tensor X tensor X. And so even easier derivations can be done for when the second or third qubit is Z, because no X's even appear. So what's kind of the conclusion from this? What can we get from adding these three things together? We can say that if you put in three 0 or 1 qubits into this GHZ program, which of course is meant to take 0 or 1 qubits, not really interesting if you put in X for the first qubit. You'll get out this rather hard to read type, but this type does correctly characterize the GHC states. What's more interesting is what if I add another line? So I'm calling this GHC prime, and I've added one line that is going to do a C0 from 2 to 1, and that should disentangle 1 from the rest of the GHZ state, right? So fortunately, what we see is that the outcome of this middle derivation has the Z tensorized tensor I, which means, again, that Z is separable from the rest of the system. So I can now derive that GHZ prime, as I'm calling it, has the output type Z cross X tensor X intersection Z tensor Z. That's something that we've already seen. That's our good friend the Bell pair again. So we're getting out a classical qubit and a Bell pair. What if I do yet another C0, C0 from 3 to 2? Well, now you'll notice that all 3 of the outcomes contain 2 I's and 1 Pauli matrix. And that says that all of the outputs are going to be separable. So GHZ prime prime takes Z cross Z cross Z to Z cross Z cross X, and that's because it basically turned one of our 0 or 1s into a plus minus, and then it performed some convoluted swap to get the plus minus qubit into the 3rd position. So that's nice. We've just created a fully entangled state, and then we completely unentangled it. The last sort of interesting, or maybe most important question is, can we extend this beyond just the Clifford set? Because the Clifford set, again, isn't universal and it's not comprehensive, and we knew we could simulate it. So let's try adding T. Well, we saw earlier that, S had this, our Z type is anything that's in 0, 1 with some modulo some phase. So T also has type Z to Z. Unfortunately, it has type X to top. And by top, I mean you're leaving the Clifford set, right? And top is going to be something that encompasses all of our other elements. So that's a little bit risky. And it sort of asks us, hey, can we do anything useful with T's? And well, I tried the most obvious thing, and it actually worked out really well. So, the other way we can make a universal set is adding Toefl. We know how Toefl behaves on certain qubits. Let's see if we can derive that. So here's Toefl on where the 3rd qubit is an X. So applying an H will turn the X into a Z. Applying a C0 will propagate that Z. Then applying a T dagger, which has the same type as T, will do nothing because we're applying it to a Z. Again, propagating a Z, and then doing nothing when we apply the T, or at least doing nothing to the type. Turning a Z back into an I, applying a T to a Z, turning another Z into an I, applying a T to either an I or a Z, both of which again are no ops. Here we finally turn that Z back into an X, and the last 2 things don't even touch the non-I variables, so they're all identities from the purposes of the type system. So our conclusion is that if you put in an X into the 3rd position of a Toefl, you'll get out an X qubit. And here's the full list of types that we can get for Toefl. So you see 3 interesting ones. Z goes to Z in the 1st position, Z goes to Z in the 2nd position, X goes to X in the 3rd position. And then for the other ones, we do quickly bang into a T gate that is being applied to an X, and that propagates, and that says, oh, some set of qubits is some state is coming up, but we can't really characterize it. But what I do have is enough to say that Toefl has this type that if you put into separable 0 or 1 qubits and a plus minus, you'll get out 2 separable Z qubits and an X qubit. And in fact, I could have ignored the X and said for any I, if both of the inputs are classical, you'll get out this separable state. So that's pretty nice. So that's what I have to show you for now. There's obviously a lot of work that we want to do to make this more powerful, more robust. So separability is right now defined. You can only derive it from something from, Z tensor some number of i's. There are more ways of proving separability between states of multiple qubits, and we can do those using intersection types. We'd like to expand sort of more robustly beyond Clifford, so maybe have types that are between X and top. We'd like to incorporate measurement, which exists in Gottesman in the Gottesman paper that we've been building on, but it is not sort of a function of a specific, is not local in the sense that these other rules are local, which means it may not be linear time to infer the types, which is something we don't like. So we're thinking about how we can efficiently incorporate measurement. And then there's a whole bunch of applications, including resource tracking of Ebits, provenance tracking, which we can use to show that quantum communication protocols are not allowing, illicit exchange of qubits. And we also hope to use this to validate error correction codes, which has this very nice correspondence with the work that we've been doing. And that's all. So thanks so much for your time, and I'm happy to take questions.
Okay, thanks. That was a great talk. So there's already several questions from the audience, but actually I really want to ask one as well. But let's start with the audience. So Alex Kissinger is asking, can you encode the full stabilizer tableau of a Clifford unitary as a Gottesman type?
Can I encode the full what? The
full stabilizer table, let's say, or tableau. I'm not very good at pronouncing this.
I believe so. I mean, I think so Gottesman types, we were actually, so one thing that we could have done is we could have erased the plus or minuses from Gottesman's paper and only had X and no negative X, which I have done for this presentation, but we haven't done for the actual system that we've built. So I believe so. I mean, this incorporates everything that Gottesman's system incorporates.
Cool. Another question from Alejandro Diaz-Caro. What is beyond Clifford? Is it all typed by top?
So not necessarily. So one thing you can do is, so for one thing, it's, if you can add T-gates as I've shown and still be within our system, it's just, only in limited cases, like in that Toefl example I showed. And obviously that T could be generalized to any rotation around the Z-axis, and we could have something that's analogous for any rotation around the X-axis. It's not the only kind of approach. So we're talking about a basis of X and Z effectively. You could talk about things that take you between S and H maybe. And that would maybe give you more expressivity while not taking you all the way to Clifford plus T. But I mean, it is true that there is no system that can, fully characterize quantum states while still being a linear type system. I mean, that's just a fact of complexity theory.
Yeah.
It's one of the big questions is how far can this take us?
Yeah, actually, I have a question which is very related to Alejandro's question. So is it possible to see what you're doing as a form of abstract interpretation?
Yeah.
Yeah.
Yeah, I mean, if so I didn't wind up including this in my slides, but Simon Perdis has a paper called Abstract Interpretation for Quantum Computing or something like that, along those lines. It has those words in it, and that paper is very similar in many ways to this one. The only problem is that it only has sort of a binary entangled or not entangled, and it's conservative in that, when it says entangled, it means potentially entangled. So, and it has that sort of issue I mentioned earlier, which is that it's easy to leave the system. But yeah, so that paper has a lot in common with this one, and that one is framed totally in terms of abstract interpretation. I thought it was a really interesting read. Okay.
So Rose Duncan is asking a question. So I'm not going to read the first part, but he's saying that this could easily be done in the ZX calculus. So what is the advantage of your system?
It's not in the ZX calculus. So
okay.
This system is designed for typing quantum circuits, and the ZX calculus is a fully expressive sort of alternative to quantum circuits. So I think this is something that's useful. Like, there's obviously a lot of connections between this and ZX, but this is something that's useful in its own right as a typing system for all these languages that don't allow us to say precise things about our programs, which, you know, for the foreseeable future are still going to be written in this format of we're applying gates to things rather than we're creating spiders that are red or green.
Okay, thank you. So I think we're out of time, so we can continue the discussion in the channel, but because the next talk is pre-recorded, we really have to start now. So we should thank Robert again, and yeah, continue the discussion in the channel. Thanks.
All right, thank you so much.